All right, so in this video, we're going to walk through solving for eigenvalues and eigenvectors in linear algebra. Now, to start with, our basic equation is going to be that A, our matrix times some vector x, is going to be equal to a scalar multiple of that same vector. So we're looking for those vectors on which our matrix operates as a scaling factor and not as, performing a rotation or something like that. So now it is certainly possible that some vectors or some matrices don't do that. They don't behave that way. And we will, when we find that, we will find that out through the algebra. But many matrices do have directions in which they behave exactly like scaling factors. Now, in order to solve this equation, what we're going to do is we're going to put everything on one side and then set that equation equal to 0, and then factor out our vector x. Now, in the process of doing this algebra, what we might sometimes end up with, if we're not careful, is an expression that says A minus a constant. A matrix minus a constant is equal, can be simplified. And we can't actually subtract a constant from a matrix. And so what we do is, to make this algebra work out, is we represent lambda as lambda times a matrix I, the identity matrix, so that these are both matrices and so that you can do the subtraction. So that is designated in order to make this subtraction expression defined. Otherwise, we wouldn't be able to do it. Now, once it's in this form, essentially what we're looking for is an expression for this that is dependent, that is homogeneous. And so therefore, we're looking for a non-trivial solution to this dependent system, this dependent homogeneous system. Now, a good way to show that you've made an algebra mistake for problems like this is to end up with a vector that is all zeros, because that would mean that your matrix is actually not dependent. And if you're only getting the zero or trivial solution to the system, then that's because you've made an arithmetic mistake someplace. You'll either get a solution or you'll get a complex solution, so it may not be a real solution. But you will have to get a solution that is non-zero to this system. All right, so once we have set that problem up, then we're going to go through, we're going to find the determinant. The determinant will tell us if it's equal to 0, that the system is indeed dependent. That will give us a condition on our lambdas, and then we'll be able to go through and solve the system. So we're going to walk through a couple of examples for specific matrices to see how the rest of the process plays out in the particulars. So here we have the matrix A is 3, 2, 3, 4. And so we're going to start by finding our matrix A minus lambda I. And so we're going to do that by taking our A matrix, and then we're going to take our identity, a 2 by 2 identity in this case, to make the sizes line up. We're going to multiply through our lambdas and then subtract component by component. And so that will give us 3 minus lambda. The 2 will remain unchanged because that was a 0 that we were subtracting. This 3 will remain unchanged, and then 4 minus lambda will end up as our final component. Now, again, to get a condition on lambda to make this dependent, we're going to use our understanding of determinants. If determinants are 0, then the matrix is dependent, and therefore that will create our condition on these eigenvalues, our lambdas. So we're going to calculate our determinant. So for a 2 by 2 matrix, this isn't a big deal. We multiply our diagonals, so 3 minus lambda times 4 minus lambda, and then we subtract the off diagonal, which is minus 3 times 2. We set that equal to 0. Now here we have to do some algebra. So we're going to FOIL out our terms here and combine like terms. So 3 times 4 is 12. 3 times minus lambda is minus 3 lambda, minus lambda times 4 is minus 4 lambda, minus lambda times minus lambda is positive lambda squared, and then minus 6. And then when we combine like terms, we end up with lambda squared minus 7 lambda plus 6, because it's 12 minus 6 is equal to 0. Now, you will get the same values for lambda if you choose to subtract in the other order. So if you choose to subtract lambda I minus a, all your signs will be different in this expression, but it will have the same solution because you can just flip the signs to make lambda positive, the lambda squared positive, which if you're going to factor, you would want to have done. But I have seen some people create this convention where they're doing lambda minus 3 and lambda minus 4 here on the diagonal, and then subtract the a and get minus 2 and minus 3. It does not actually change the solution at all. So this is the convention that is typically adopted in the linear algebra books that I've seen. All right, so once we get this equation, this is called the characteristic equation of the matrix. And so now we can go ahead and solve for lambda. This equation is factorable. And so we can factor it as lambda minus 6 and lambda minus 1. Again, the minuses will get us the minus 7, but the two minuses multiplied together will get us the plus 6. And therefore, we can find our eigenvalues for this matrix as being lambda 1 is 6 and lambda 2 is 1. Now, in some introductory problems in the course, often in textbooks, they may give you the lambda values and have you find the eigenvectors from there. In those kinds of problems, this is the point at which you would pick up with those examples. Because now we have to find the eigenvectors, and there is a vector for each corresponding lambda. So first, we're going to start with lambda 1 equals 6. Now, we're going to plug that into our A minus lambda I matrix. And when we do that, we're going to have 3 minus 6 up top. So that'll give us minus 3 in that top left corner, and 4 minus 6 on the bottom. That'll give us a minus 2. Now, in 2 by 2 matrices, this becomes really obvious that this matrix is dependent because the two rows are obviously multiples of each other. Now, when you get into larger matrices, it's less obvious. And you'll see that it's a little less obvious when we use complex numbers as well. But if we haven't made any arithmetic mistakes, then these will be dependent systems. And when you row reduce them, you will have to get down to one row equal to 0. Now, for larger matrices, when you don't have complex numbers, you can do the row reducing for individual lambdas in your calculator. But do kind of keep in mind that if you don't end up with a row of zeros, or obvious multiples of each other, that there is a problem with your arithmetic, because if this is not dependent, you've made a mistake either in simplifying or in finding your lambdas. Now, because these are obviously dependent of each other, they're just multiples of each other. The top one minus 1 gives me the bottom one. I only have to use one equation to satisfy the entire system. And so I'm going to pull out the bottom one just because it leaves my sign positive here. So I get 3x1 minus 2x2 is equal to 0, because remember, our system is homogeneous in this configuration. And so that means that 3x1 is equal to 2x2. And the relationship between x1 and x2 is that x1 is equal to 2/3 x2. And since x2 is free, I can create my solution as being 1 in my x2 component, and whatever this coefficient is in my x1 component of my vector. And then whatever value I choose to make x2, then I can rescale this vector so that I can get whatever I want. So if I designated x2 to be 10, then 1 times 10 would give me the value for x2, and 2/3 times 10 would give me the value for x1. Now, I can also choose x2 in a way that makes these numbers nice whole integers. So if I chose x2 to be 3, for example, then 2/3 times 3 would just give me 2 in the upper component. And so I want to normalize my vector. Typically for eigenvalue and eigenvector problems, I do want to make sure that I get whole numbers. It just makes the math easier to work with later rather than having to work with fractions. So the process of normalization is basically just to make sure that you have vectors that are small integer components as much as possible. Now, you could also normalize them in the traditional sense of making them a unit vector. And there are contexts in which this is what you would prefer to do. In this case, 2 squared and 3 squared gives me 13. So this would be 2 over the square root of 13 and 3 over the square root of 13. But in most cases, it's actually just more convenient to work with small integer components rather than actual unit 1 vectors or vectors of this sort. So normally when we talk about normalizing in this context, we mean try to get rid of your fractions and just work with small integers. Any multiple of this vector is going to be an eigenvector of this original matrix. So we just pick the one that is the easiest to do arithmetic on. And then we have to repeat the same process for our other eigenvalue. So we set lambda 2 equal to 1, and we plug that into our matrix. So here we're going to get 3 minus 1 on this component, which will turn into a 2, and 4 minus 1, which will turn into a 3. And again, we can see these are clearly multiples of each other. And I can pick either equation that I want to solve. In this example, I picked the top one, smaller coefficients. I don't know. But here 2x1 plus 2x2 is equal to 0. Remember, our system was homogeneous. And so we solve for x1 in terms of x2, and we end up with x1 is equal to negative x2. And so because x2 is free, the x2 component of our solution vector is 1, and the top component of x1 is just the coefficient from our equation here. So this doesn't need to be rescaled. Our second eigenvector corresponding to lambda 2 is negative 1, 1, or you could flip it. You could make it 1, negative 1. Again, any multiple of this vector is fine. So these are often referred to collectively as eigenpairs because the eigenvalues and the eigenvectors go together. So you would have to specify lambda 1 equals 6, v1 equals 2, 3, and then lambda 2 equals 1, and v2 is equal to negative 1, 1. We usually use the same subscript for them to indicate that they go together because they do go together in pairs. The idea here is that if I take my A matrix and I multiply by a multiple of the v2 vector, that the matrix is going to act like a multiplier of 1, which means it's not going to do anything in this for vectors in this direction. If I multiply it by my 2, 3 vector, then it's going to act like a scalar multiple of 6 every time I do the multiplication. So they go together. They're not interchangeable. Now, if we do a 3 by 3 matrix, we do have to be a little bit careful because doing row operations on a matrix changes the eigenvalues. So we can't use that process to simplify in any way. At least not until we have individual eigenvalues already. So if we start with a 3 by 3 matrix, we're going to end up here in our example. I've picked some that have some zeros to make the algebra a little bit easier. But here we end up with our a minus lambda I, 3 minus lambda, negative 1 minus lambda, and 4 minus lambda on the diagonal. And then we have to go ahead and find our our characteristic equation. All right, so because our middle row of our matrix has 2 zeros in it, I'm choosing to expand upon this middle row position so that we'll have the least amount of algebra to do. Now, in this particular case, remember this is a plus minus position, and then this would be a plus position, and this would be a minus position. So the zeros and the two minus positions disappear, and I'm left with canceling out this column and this row, and my submatrix that I have to multiply this -1 minus lambda with is the 3 minus lambda from up here, the 2, the 0, and the 4 minus lambda down here. And then when I calculate this determinant, I get these two minus 0. And so I'm left with this equation. Now, this is already factored because of the way that we chose all the zeros in our matrix. If you are working with a slightly more general question, if you may want to try to factor out something in common depending on where your zeros are. However, you may have to FOIL everything out and then recombine things and hope that you are able to factor it from that point. It is kind of a tedious process, honestly, for random three-dimensional problems. But in this particular case, don't FOIL it out because it's already factored. And so we already know that our eigenvalues are going to be -1, 3, and 4 just from having it already in this form. Now, typically textbook problems will not give you problems that cannot be solved, where you get really insane values for all the eigenvalues and eigenvectors. So you should be able at some point to be able to factor it, or they wouldn't give you the problem. But in general, cubic problems like this are much more difficult to factor than quadratics. If you have complex zeros or things that involve square roots, again, it may be difficult to find the exact values. Not impossible because they're all solvable. There are formulas for solving for roots of cubes, of cubic equations, but nonetheless, they are more challenging than the regular two-dimensional examples. Now, all of ours are real, and so from this point, we are going to have to find the eigenvector in the null space for each of our A minus lambda I matrices. So if I plug in, starting with my lambda equals -1, then I'm going to get this matrix. Now, in this particular case, I have a row of zeros already, and then I can further reduce this matrix using my calculator to get this expression. So my equations are going to be x1 is equal to x1 plus 7 over 24 x3 is equal to 0, and x2 plus 5 6 x3 is equal to 0, and then x3 is equal to itself as my free variable. And when I move all of my x3s over to the other side of the equation, I get these coefficients. And if I want to normalize this in order to make all of my solutions integers, then I'll multiply by 24. I'll let x3 be 24. And so that will give me just the -7, -20, and 24. So again, even though my matrix wasn't that difficult because I had all those zeros in it, I still ended up with a weird looking eigenvector. If I do the same thing for my other two eigenvectors, so here I'm going to plug in my lambda equals 3. This is going to give me this matrix. I have a column of zeros this time. And so if I row reduce my matrix, I get this. Now, remember what this means is that, again, x2 is equal to 0, x3 is equal to 0, and then x3 is free, which leaves me with this as my eigenvector. And then finally, if I do lambda equals 4, then I'm going to plug in my 4. I'm going to get a -1. -1 minus 4 is -5, and 4 minus 4 is 0. I get this matrix. And if I row reduce this, I don't have a row or column of zeros, but if I row reduce this, I get this matrix. And remember, this means x1 minus 2x3 is equal to 0, x2 is equal to 0, and then x3 is equal to itself. And x2 is 0. That gives me a 0 component here. And the coefficient of x3, when I move it to the other side of the equation, is 2, and the free variable is 1. And so I get 2, 0, 1 as my eigenvector. Now, the set of solutions to an eigenvector problem like this is called the eigenspace. So the set of vectors, that is the eigenspace. If you have enough vectors for each dimension of your matrix, then that eigenspace will be the same as R3 in this case, or R2 in our previous case. Sometimes when you have repeated values, you don't get 2 eigenvectors for the repeated eigenvalue. And so then you don't have enough to span the entire space. So our third example, we're going to be looking at this 2 by 2 matrix. And this one's going to be a little more complicated because this equation, the characteristic equation we get is not factorable. But when you get square roots in your equation, you're going to be able to actually shortcut a little bit of the algebra, even though the algebra you do have to do is a little harder. And your calculator will be much less useful unless it's like a TI-89 and it can handle exact square roots, because the TI-84 can't. And in fact, if you get square roots and you try to do these in your calculator, your TI-84 is almost certainly going to have a rounding error that is going to screw up your entire problem. So not just give you just not give you decimals, but actually give you a bad solution. It'll claim, because of rounding errors, that the matrix is not dependent, that it's actually independent, and your vectors will end up being 0. So don't use your calculator if you're using a TI-84 to solve problems where you have square roots in them. You're going to have to do them by hand. Now, in this example, again, we're going to find our eigenvalues by subtracting lambda off our diagonal and then finding the determinant. So we get 1 minus lambda and 1 minus lambda, and then we have 3 minuses, so this is still a minus 12. And then we FOIL out our binomials, and we end up in the end with lambda squared minus 2 lambda minus 11. And I cannot think of any factors of 11 that have a difference of 2. And so we use the quadratic formula, and we end up with this expression with 1 plus and minus 2 square root of 3. Now, again, you can still do this. Pick let's say the positive version, 1 plus 2 square root of 3, and we start solving just as we did before. So 1 minus 1 plus 2 square root of 3, don't forget to distribute your minus sign. Same thing down here, and you end up like this. Now, it is less obvious that these equations are dependent, but they actually are. If you, in fact, were to, for instance, multiply by the square root of 3 on both sides of the equation, it would be more obvious on both sides, let's say, of this bottom equation. It would be more obvious that these equations are, in fact, multiples of each other. But we're going to just take one of these equations, and I'm going to choose the bottom equation so that I don't have to divide by a square root. So here I'm going to take my negative 4x1 and minus 2 square root of 3x2. I'm going to move my 2 square root of 3x2 to the other side of the equation, and I'm going to end up with x1 equals negative square root of 3 over 2 x2. Now, again, I would prefer, I can't get an integer out of this, but I can rescale it so that at least I don't have fractions. And so I'll let x2 be equal to 2, and I will get this expression. There isn't any way to really make this look nicer than this. Now, when you do the same process for 1 minus 2 square root of 3, the conjugate of our first solution, you subtract on the diagonal, make sure you distribute. You get a matrix that looks very similar to the previous one, except our diagonal elements are now positive. And if you go through the whole solution process, you are going to get this exact solution, which is just the only difference here is that the sign of the square root changed. And so our second, well, this should actually say V2, is the square root of 3 over N2, instead of negative square root of 3 over N2. Now, when you do these solutions that have these square roots in them, because the only difference between the two components is the plus square root versus the minus square root, when you solve one of the equations, you can just simply designate that the other solution is the negative in front of the square root solution. So you don't have to go through the whole algebra again. It will always work out that way. So even though working with the square root the first time is more difficult, it does save you having to do that entire second step because it will just come out with that conjugate solution. So the thing in front of the square root, just flip the sign, and that's your second solution. Now, when we start working with complex problems, we will also use that same trick because the complex ones are going to work the same way. I is just the square root of -1. Now, in this case, this matrix is already dependent, and that means that one of our lambdas is going to be 0, and then the other one will be something else. But we're going to go through this problem starting out with the same process because we still need to know what that other lambda is, and we can only get it by going through and finding our characteristic equation. So we'll subtract lambda off our diagonals and find our determinant. And when we distribute everything, we end up with 1 minus lambda and minus lambda equal to 0. And that means that our eigenvalues are not only the 0 from the fact that the entire matrix is already dependent, and also 1. So when we plug 0 in, we just get the original matrix. We solve for that null space, and that means we take our top equation, x1 plus 2x2 is equal to 0, or x1 is equal to -2x2, and our vector is then going to be -2, 1. For the second one, we're going to plug in our lambda equals 1. That's going to make our column 0 instead of our row 0. And when we, again, these are dependent, they're obviously multiples of each other. So I take my last equation that says x2 is equal to 0, and x1 is the free one because that's the column that has the zeros in it. And then that's going to give us an eigenvector of 1, 0. Now, so far, we've only been looking at real solutions, but let's look at the complex solution, and we'll see that it has some similarities with the square root case. So here is our matrix that we're going to be working with, and we're going to, again, start the same way by subtracting lambda off the diagonal and finding our determinant. So -2 minus lambda times minus lambda minus 2 times -5. And when you FOIL all of that out, you get characteristic equation as being lambda squared plus 2 lambda plus 10 equals 0. Now, this is obviously not factorable. Again, I can't think of any factors of 10 that have a sum of 2. And so I'm going to use my quadratic formula to get -1 plus and minus 3i. Now, again, I'm going to pick you can pick either the positive or negative version. It doesn't really matter. But I'll pick the positive version for lambda 1, and I'll plug that into my A minus lambda I matrix. Again, don't forget to distribute your minus signs. And so -2 minus the quantity minus 1 plus 3i gives me minus 1 plus 3i. And then in the bottom here, it's just flip all the signs, 1 minus 3i. Now, again, this doesn't initially look like they are multiples of each other, but it actually turns out that they are. Now, so you don't have to try to further row reduce them. It is very common for these complex eigenvalue problems to have similar values in the two diagonal entries, particularly for these 2 by 2 cases, but with the real part having the sign flipped, not the complex part. So they're not conjugates of each other, but it's the real part that has the sign flipped. So what I'm going to do is I'm going to take one of these equations and just, because it, again, if I've made no arithmetic mistakes, it should be dependent. I'm going to take the bottom equation so I don't have to divide by I and continue with my solution. So I have my minus 5x1 plus 1 minus 3i, all of that times x2 is equal to 0. I move my x2 over to the other side of the equation. Again, I don't want to divide by I because that makes the math harder. I have to rationalize in order to separate the real and the complex parts. And here I'm not dividing, so I don't have to worry about that. And then I divide by my -5, and I end up with x1 is equal to this crazy 1 minus 3i over 5, all of that times x2. The real part of this coefficient is 1/5, and the imaginary part of this is -3/5. And so I get my vector is going to be the 1/5 and -3/5, and then 1 in the next component. I can then designate x2 to be 5 in order to get nice integer values instead of nasty fractions. And then when I go to solve for my other eigenvalue, I'm just going to take the conjugate of this one and flip all the signs. Now, it is very common for problems like these where you are trying to solve these problems where you actually want the real and imaginary parts separated. And so once you find your version of the solution like this, then you can separate out the real parts, -1 and 5, and then separately -3 and 0, or +3 and 0, whichever one you're working with. And there's actually applications for these for rewriting, for instance, your matrix as a rotation matrix. How is it being rotated and scaled? If you have complex eigenvalues, that's essentially what's happening, is being rotated by an angle and then being rescaled. And you can figure out what that angle of rotation and that scaling factor is, but you'll need your eigenvalues in this form.